really good electrical engineers and mechanical engineers, because not that the physicists are going anywhere. Like, there'll always be, I think, room for really smart physicists and really smart computer scientists in this field. But as the field matures, it's going to be maybe less of a hard science and more of an engineering problem. And there are so many interesting and challenging engineering problems that we still have to solve. So we're not quite there yet, but that's something that I'm really interested in seeing explode in the next 5 to 10 years.
Can you share more about the status of quantum hardware? And where is IBM now? What do we expect for the roadmap? What is
Yeah.
fault-tolerant quantum computing and how to get there and when?
Right. So just for a little context, so fault-tolerant quantum computing is quantum computing that aims to build a universal quantum computer. So that's a quantum computer that has error correction implemented in it. So it's a quantum computer that's big enough that we can correct for errors basically when they occur, because the qubits are so prone to noise and errors and stuff like that. And these are the quantum computers that, if they were big enough, would be able to run the algorithms that maybe are most famous, like Grover's algorithm and Shor's algorithm. And nobody's there yet. But IBM does have a roadmap to scale up to that size in the next, I think it's 10 years. We have a roadmap that you can look up, and it's published. Um, where we are right now, our current largest chip, I believe, has 100, or the chips that we're building now, the largest chip that we've built has over 1,000 qubits. But right now what we're working on is building chips that have about 130 to 150 qubits on them, and figuring out how to make them modular so that we don't have to build one big chip with 1,000 qubits, but we can build a few smaller chips with 100 something qubits and connect them with couplers. So we're studying how to create those couplers now and make them with really high fidelity so that there's no loss of information when information travels from one chip to another. So that's currently the biggest problem that we're working on right now. That's sort of the state of the hardware.
IBM uses superconducting qubits, transmon qubits. What do you see as the advantages of it, but also the challenges?
Yeah, so I love transmon qubits because they're so simple from a mathematical and physics standpoint. They're the easiest thing to build also. If you've ever worked at a fabrication lab like I have, simple is good. Complicated is not so good. It's really, really hard to scale complicated builds, which is why I love superconducting transmons, because they're so easy. And the advantages of building transmods are that you have all of the infrastructure already needed to build them, basically, because the same machines that you would use to build semiconductor processors can be used to build superconductor processors. So you don't have to build up this whole multi-billion-dollar fabrication industry, which would be a huge challenge to overcome, I think. You can just use the same machines that already exist. So that's really a huge plus. Saves a lot of money and time and infrastructure that you would have otherwise. Um, the negatives of transmons is that they're very prone to noise and they can decay quickly. But we've seen a really pretty big shift and a lot of progress in that area as well over the past few years. We've built qubits that have over, hundreds of microseconds of coherence time. And, that still sounds relatively short, but we've gone up by a factor of 10,000 in time since I was in, early graduate school. So it's progressing really, really fast. So I'm very optimistic about this technology scaling even further.
That's fantastic. And just a heads up to everyone, some of these famous algorithms that Olivia just mentioned, we will learn very soon. On Friday, we will discuss Grover's algorithm, and it will be discussed more next week. And then, if you want to learn more about these transmon qubits, go to the module 3 on Canvas and go to superconducting quantum computing there. There you will find a very good lecture from Kyle Cerniak from MIT Lincoln Lab, hosted last year, where you can learn all the basics of superconducting quantum computing, including transmon qubits.
Kyle is fantastic, by the way. I know Kyle, and he's just
Yes.
A+.
Great. There was a question about quantum computing combined with how you entered physics, namely from Gautam Kamar from India. How will quantum computing be useful for astrophysics and cosmology? Do you have some insights on that?
I don't think anyone has really been poking around in that space too much yet. So this is an area that we could definitely use some experts like I talked about in that
Okay.
specific domain area, because I could definitely see some sort of processing being useful, because anytime you have a ton of data, big data, we look for ways to optimize sorting the data and try to pick out specific signatures or clusters out of what look like just a bunch of random signals. And quantum computers are pretty good at that. So, I could definitely see this being applied to like a dark matter search, or I don't even know, like there are some quantum principles that go into supermassive black holes. I'm not an expert in that, but maybe we'll learn something by building the quantum computers that will apply to general astrophysics as well.
Exactly. What do you see as other application areas besides astrophysics that could be interesting in the more near term?
Yeah, so I think in the near term, what you want to think about are things that are chemical in nature. So that might include battery development or green energy or material science, trying to build a stronger, better material for some sort of specific application. Any of that kind of thing is what we're looking at in the near term, because what quantum computers are really, really good at just intrinsically, and you don't necessarily need thousands of qubits to do it, is to simulate an atomic lattice and to simulate interactions that happen on the molecular scale. And it turns out classical computers, even supercomputers, are really, really, really bad at that. And I think I read that like 40% of all time that's booked on supercomputers are built to try to, or a book to try to simulate chemical interactions, which is like why batteries haven't gotten better in the past 2 decades. Basically, it's just sort of impossible. It's too much guessing and checking. Um, and if we could try to develop, models to simulate these interactions before we had to go to the guess and check method, hopefully this would improve a lot faster.
Great. Then to a question from Noga from Israel. Can you share more about error correction? How does it work? What is IBM's current state for error correction? And then, do you believe superconducting qubits will be the end game of quantum computer hardware? Oh, Noga is getting serious.
All right, yeah. So error correction, basically the idea is that you have a qubit in the middle of your processor surrounded by a ring of other qubits, and those qubits are used sort of as test qubits, and they can tell when your center qubit that's actually processing an algorithm has an error occur, and it can detect it and basically correct for it in real time by seeing if it's the same answer that it was supposed to have calculated compared to all of the other qubits on the outer ring. So that's the basic idea of error correction. IBM published a really interesting paper a few months ago that showed that actually the amount of qubits that you need in the surrounding outer ring is a lot fewer than we previously had thought, which is a really big deal, because previously if you think you need, 10 qubits to your one computational qubit, that scales pretty badly, because then you actually need 10 times the amount of qubits as you might think. And it turns out we figured out that we actually need quite a fewer number than we thought. A large percentage was able to be, chopped off the top. So that makes it scale a lot easier. So that's what we're doing right now. And do I think that superconducting transmon qubits are endgame? Yeah, I think I do. I don't necessarily know if I would bet my money on superconducting qubits becoming the only hardware that anybody uses. I could see multiple modularities sort of winning in the end, or maybe being suitable for different types of applications. But I think that superconducting qubits are definitely going to be one of them.
Great. Then a very good question from Kush. Kush says, considering qubit interactions can also introduce errors in quantum chips, how does IBM address this challenge in their superconducting qubit architecture?
Okay, I have to be careful how I answer this, because I don't want to give away any company secrets.
Yes.
But basically, there are interactions that you can turn on or off depending on what specific frequency you're sending your measurement pulse with. And if you send it at a frequency that some of the qubits basically don't interact at, then it's basically like they don't see that signal at all and they don't see that interaction. So if you keep the right frequency and you stay in like the right bandwidth, and you keep it far away from like the qubit interacting frequencies, then you don't have to worry about it. So we just have to make sure that when we calibrate our measurement tones, we're in the right bandwidth.
Thank you. Then there is a question about the current status of hardware translated to applications. Sunil Karki asks, can we make simulations of bigger molecules with the current state of the hardware?
So not yet. We're not at the point where we can simulate bigger molecules than we could with a classical computer. But we're getting to the point where there could be some interesting science to be found at the scale that we're doing now, because it's not just about making bigger molecules, it's about looking for more accurate results and more accurate interactions. And we're right at that point now where we're sort of able to compete with some classical computing techniques, maybe not all of them. Turns out classical computer scientists are very smart and they've been doing this a really long time, so they have a bunch of tricks and tips they can play. And we haven't quite beaten all of them yet. But we're at the point where you can use quantum computers as another tool to verify your model or to verify a solution. Because when you're simulating something, before you go and you actually like test it and make that environment in the lab, you don't know what the right answer is. So we might use a classical method that might say like, oh, the ground state of this molecule should be 6. And we might have a quantum computer that says, I don't know, actually, I calculated that it's 7. And we might need another supercomputer that says, actually, it's 5.5. So when we have another tool that we're able to use to sort of verify that we're on the right path and that all of our answers are sort of coalescing into like the same order of magnitude, we really have something here.
Fantastic. And everyone, thank you all for the great questions. There are really many questions coming in. Feel free to upvote other people's questions so I can see which questions really need to be asked, because all of them are really good. Thank you. I see also some really advanced or specific questions that you are all invited to really dive into yourself, because quantum is a developing, evolving field right now. And some of the applications have hardly been explored, especially as we are developing the hardware to get to that stage where there is an advantage. I saw a question about, let me scroll back. Yes, an interesting hardware question from Sanjot. Sanjot asks, how would room temperature superconductors affect the development of superconducting quantum computers? Do you have insights on that?
Yeah, actually it wouldn't. I know a lot of people are really disappointed by that answer, but we don't care about room temperature supercomputers for what we're trying to do. Our technology is cold for a reason, and it's not just because we want to keep the supercomputer cold or the superconductor cold. It's also because we need to get rid of all thermal noise in the environment. So it wouldn't actually help us, unfortunately.
Thank you for these clarifying insights. I will scroll. Yes, a good general question that is useful to know for all the upcoming weeks. People use a lot of terms like quantum advantage, quantum supremacy, quantum utility. What is the difference between these? Is what Nandan asks.
That's a really good question. So quantum advantage is like the gold standard. Quantum advantage is basically like when you can do something on a quantum computer better in some way, either it's faster or it's more accurate than any classical computer could do. And we're not there yet. That hasn't happened. Quantum supremacy is sort of ill-defined, and it's this idea that like any process can be done on a quantum computer faster than a classical computer. So that was shown to be possible for random number generation. So like, yes, quantum computers can generate random numbers more accurately or faster than a classical computer, but like there wasn't anything you could do with that. Like it was an interesting experiment, but it was totally not applicable to anything in the real world. And then quantum utility is sort of what I was talking about earlier, where quantum computing is an option for verification to compete with brute force methods. And it's sort of just, we're at this point right now where we're like, oh, it's useful for scientific discovery, but maybe it hasn't become a product yet, like it would for quantum advantage.
Thank you very much. That is very clear. Then a question from Yazid from Palestine, asking, can you compare the field of quantum and the field of artificial intelligence? And Jazid asks, how do the current capabilities and limitation of quantum computing compare to those of artificial intelligence? And how do you see the trajectories in technological advancement?
Yeah, it's a really big question. So I guess first of all, the thing to know is that AI and quantum computing, I know a lot of people think they're dueling with one another right now, but they're really totally different technologies because we've been working our way up to AI and large language models for like the past 40 years. It's just like the next step in classical parallelization of computing. It doesn't really like change the game necessarily. It's using the same basic laws that we've been familiar with since computing became a thing. Quantum computing, on the other hand, opens a whole new avenue and a whole new window into a different type of computing because it simulates with different actual physical laws. So it's not like, oh, well, now that we have AI, we don't need quantum computing or vice versa. They do totally different things. And I think that that's one thing that I want to emphasize to you all. Now, I know AI is really, really hot right now. Like everybody knows, NVIDIA is taking over the world, GPUs to simulate AI and large language models. Like it's great. But it's not quantum computing and it won't be quantum computing and it won't ever be able to do the things that the promise of quantum computing will be able to do. However, we do see ways that they could play with one another and help boost one another. So for instance, we have a new technology right now that's coming out called the AI Qiskit Transpiler, which basically uses AI features to more accurately predict and suggest a circuit and transpile it and optimize it for you for a given processor for a specific purpose. And we found that not all the time, but often it can suggest a better circuit that's more optimized than the non-AI transpiler would. So in that way, AI is helping quantum computing. And in the future, we hope to see quantum computing help AI. There are some things that we've been exploring in the quantum machine learning realm where you can basically add a whole other dimension to your exploration space, which gives you more ability to create cuts and planar distinctions when you're doing categorization or grouping. And so maybe that could help with large language models in the future. I don't know. That's a little bit further out. Nobody's doing that at any big scale yet, but there's many interesting possibilities. So I think, the important thing to note is that AI sort of had, a path, a trajectory that went up and down for a while too. Like AI had a winter where basically there was a whole lot of people that were like, it's never going to work. We're never going to have AI. Let's just stop funding it for 10 years. And it turns out that was a mistake, right? Because if we had kept funding it, we could have had all of the technologies that we're seeing now, like with ChatGPT, a lot sooner. And, you could argue from an ethical standpoint, maybe we weren't ready for them. But again, another discussion. But I think the important thing to note is that progress is not linear, right? You're going to see some ups and downs, and you're going to see some people who are like, oh, it's working. Oh, it's never going to work. Oh, it's going to work tomorrow. No, it's never going to work. And like, there's going to be a lot of noise in the field before any trajectory can really be seen.
Yeah. And there are also some models for these hype cycles. If people are interested, also look up the Gartner hype cycle, how that went for AI, where are we currently for quantum, and of course there are a lot of nuances to these models. But since there was a lot of funding for quantum the recent years, I personally definitely think that a lot of progress was enabled to accelerate us on this hype cycle. There are a couple of questions about the IBM Qiskit program and becoming an IBM Qiskit advocate. Could you share a little bit more about that?
Yeah, so the IBM Qiskit advocates are basically people who have some experience programming in Qiskit and have shown to be a leader in their community or at their university or wherever they are right now, and they want to help basically get people excited and interested in programming quantum computing and using Qiskit. So you can apply once a year. We do an application where people can basically take a quiz and then fill out basically just a sheet that says what they have been doing, what they've been working on, and why IBM should recognize them as an advocate. I did it a few years ago. I know the process is a little bit different now, but it's pretty straightforward. And basically, if you're excited about this technology and you have some experience programming, I definitely encourage you to apply. I think it offers you a lot of benefits, and it can be a really great way to get connected with people who work at IBM or other people working in quantum computing, and you might not necessarily have access to them otherwise.
Wonderful. Then there are a lot of questions about specific applications, more questions about how to really sculpt their own career path. There was one interesting question. The question is, how to be Olivia Lanes?
You don't want to be Olivia Lane. I really, I want to put this out there because people always say like, how can I do what you do? And like, how can I follow your path? And like, this is a bad idea. Don't do what I did. I came here by accident. It was a mistake. It was not on purpose. I didn't have a plan. And so I don't know how you can replicate that or why you would even want to. You know, follow your own path and figure out your own things that you're good at. I just found this path and found this job because I tried this thing and I was like, oh, nope, don't like it. Let me try this thing. Oh, no, I'm not good at that. Let me try this. Nope, still don't like it. And I just basically was a pinball bouncing through life, just making, you know, the best educated decisions that I can based on what I like and what I'm good at. And I super encourage you not to follow anybody's path, but to just do that same thing for you. And you might end up somewhere that you didn't even think of.
Perfect. I receive messages of people saying relatable or so we should make mistakes. Yes, find your
Yeah.
own path, explore.
Oh my God, yeah. Do you know how many things I tried that I was like, that sucked. I don't want to do that again. I think that's human nature. And if you're not finding those things, you're not exploring enough.
Exactly. Fantastic. I will browse through all the questions to get to some final questions. Are there some things that we skipped, Olivia, but that you would really like to be asked? Or something you would really like to share?
Oh, geez. I don't think so. I know we hit a little bit of everything. I guess one thing that I'll caution people on, especially younger students, because it can sort of be hard to tell like when announcements come out in the field, like how big a deal is this or like how exciting is this actually? Is it just a, you know, a marketing message or is it actually like a new scientific step? I would say just find a few people in the field that you trust, that you know are, you know, that have good integrity scientifically, and follow them. Follow them on LinkedIn or Twitter or whatever other platform, you know, you prefer, and listen to what they're saying and listen to what the experts are agreeing upon. Um, you'll see, you know, all sorts of people pop up and be like, I mean, I see this even in the past like 2 days. Someone was like, I ran Shor's algorithm. I've achieved quantum advantages. Like, no, they haven't. Like, they're, for lack of a better word, lying. So be careful of that. And, you know, even if you're not at the level yet where you can use your own technical expertise to really, you know, sort through the weeds, find a few people that you trust, reach out to them if you're curious, or just follow them and see what they're discussing and what they believe.
Great. And there are indeed multiple questions about that. For example, Rishwan asks, can quantum computers crack crypto encryption, or is this just a myth? What are your thoughts on that now and for the future?
So there are some crypto algorithms that are vulnerable to quantum computing. Not all of them, but some of them are. However, that's like so many years out that I'm not worried about it.
Exactly. Um, Great. There are many questions, which means that people, you are in the right place. We will have 10 weeks to go to learn about all of these. There are also some questions about comparing superconducting with photonic quantum computers, many about specific applications, whether it's in bioinformatics or for the brain or for agriculture. And maybe let's do one last question about really the skill set needed. Natasha from the UK asks, what kind of skill sets are required to jump into the quantum industry? Could you give some last career advice, share about the skill sets and people's paths?
Yeah, so I like I mentioned before, it really matters where in quantum computing you want to work to develop your skill set. But in general, I think the best things that you can do for your career are to learn how to have some technical chops and to be able to read through scientific papers or at least press releases yourself and understand like what they're saying and even more importantly what they're not saying, what they're leaving out. and be able to explain it to other people. Like you should practice explaining what you understand technically towards people who are not technical or might have a different background than you. I think a lot of my success came because I was just really good at teaching, basically. And I was good at basically being a translator of really dense, boring scientific literature and translating it into things that people understand and the layperson might actually care about. And I think scientists have been neglecting that skill and haven't really been practicing it for a long time. Not everybody, but a lot of people. And on the other side of things, I think there's a lot of non-technical people who are afraid of sinking their teeth into the technical aspects of it because they think they might not be capable of it. And that's false too. So I really think there should be a better merger of what we might say are soft skills or business skills and technical skills. And you want to be in the middle. You don't want to be too far on either side. You really want to have a good balance of both. I think that's my best career advice.
Like, then last question from Negar from Turkey. When will the next Kiskit summer school take place?
It is taking place in July. Yes, I think it starts July 15th and signups are going to be very soon. So just keep checking LinkedIn and Twitter. We're going to make the announcement in like a week or two.
Fantastic. Olivia, thank you so much. This was a great conversation and great Q&A. Thanks to everyone for sharing all these great questions. And Olivia, thank you for being ready to answer all of these. Let's keep in touch. And you are on Discord now as well. So we look forward to keep collaborating and then have a great Kiskit Summer School and all the other endeavors.
Yeah, thank you so much. Thanks for having me, guys.
Thank you very much. Everyone, thank you for all the great questions. We will have a little break now, and then we will enter the second part of this session, namely the Q-Bronze second lecture with Gibran. But I would like to take the opportunity now to also introduce one more team member, Jasmine, who has been answering lots and lots of your questions on Discord. We just added your spotlight, Jasmine. Would you like to introduce yourself to everyone?
Oh, hello. So I am Jasmine. I did the Womanium Quantum program last summer and really enjoyed it, and I was very excited to come on as a volunteer and help them do more of that in the future. So here I am again, messaging all of you like mad. You are wonderful souls, so we will get all of this resolved. But yes, my background as far as quantum, I got into it in high school. Towards the later part, I knew I loved computer science at that point, and I loved physics and AP physics. And then I heard about quantum computing from a sci-fi teen novel, and I thought it was like, oh, this is a plot device to keep the book moving, right? Like that's kind of too cool to be real. So I Googled it. It's like, no, it is real theoretically, and I thought that was amazing. So I looked into it more and I loved it. And as I went through college after that, I took any chance I could to study and learn about it more through books and courses or classes at my college. And now I'm a software engineer by trade and a quantum enthusiast hobbyist by passion. So that's what I do.
Amazing. And Mohammed Ali from Iran says Jasmine is a perfect team member. I agree. But also, if there are still things you want to say to Olivia Lanes, like some people express thank yous or other things, please keep putting it here and we will share it with Olivia. And then can keep collaborating even more and having her back in maybe even this or next programs. IVM from the US says, me too, software developer and quantum enthusiast. Great. Feel free, everyone, to take a brief break now. I will bring up the break slide to make it clear to everyone. Here we go. Should be sharing screen right now. And then in a few minutes, we will start the next part with Gibran. How's everyone doing? We had the launch yesterday. Now second part, diving more into quantum computing, soon quantum programming. Is it going well? Are things becoming clearer? What to expect in Canvas, elsewhere? Are things confusing or not? The break will be 5 minutes until 0.20. So until 9:20 a.m. for me, 11:20 Eastern. I think in like Pakistan, it might be 8:20. Please translate to your own time zone. Yes, the lecture will start in 5 minutes. And in the meantime, you can take a break and we will just do some more Q&A, get some feedback from you, see how Gibran is doing. Great, I hear for Annika things are going great. Robin from Bangladesh asks, is today's session all about discussion? And no, very soon, in 5 minutes, we will enter a lecture by Gibran Rashid on quantum computing and programming. And this will be in-depth, some mathematics, physics, programming. Yeah, this is a good question from Mohammed Ali, quantum computing for bioinformatics. We will have a lot about quantum applications also in the upcoming weeks. So definitely keep this in mind while you start exploring quantum algorithms yourself, how it could be useful to your field or to other fields that you find interesting. I see some people raise their hands on Zoom. Please ask your question on Discord. The link to join Discord is in your welcome email. That one has been sent from the quantum@womanium.org account. If you only signed up maybe on Sunday or yesterday, you might not have received that email yet, and it will come tomorrow or within 2 days. That one guy says, nickname that one guy, please, by the way, change it to your real name and your country, because then we can all get to know each other. But very good question. Gibran, we hope all that your mom is getting better, and yeah, and I'll express our thoughts and wishes to her. Rafael from Ghana asks, should we start learning about quantum computing on the Canvas website? Canvas is one of our main learning platforms. So we have Zoom for the live lectures, plus a YouTube live stream. Then we have Discord for all communication, announcements, discussion. And Canvas is where you find all the exercises, links to the lectures, and also more guidance on how to walk through this program. For example, and I can show you briefly, I will bring up the dashboard for the quantum program and show how this can help you. This is how you should see it. The most important tabs are home and modules. If you go to the home page, you see an overview of the modules. And for the modules that we are currently doing, you see the qualifications needed to earn a certificate. So you can really show that you put effort in this program. Then modules is the main part. Just start from the top, from getting started. There you fill out more about yourself in the pre-program survey. You do the pre-program quantum level assessment. Please do this with your current status of knowledge. So it doesn't matter if you score low, for example. We just hope that in the end quantum level assessment after the program, you score higher. So we see that you made progress this summer. And then here in Get Started Launch Session, we just added the slides from yesterday and also the recording from yesterday. So you see that here from top to bottom, you can walk through 2 optional modules. You can play the Quantum Odyssey game here. We will have a demo tomorrow, and you can prepare yourself better, learn more about quantum mechanics, and learn more about the quantum computing basics. And these are both one lecture and then a short quiz for yourself to learn better. And then you get to the Q-Bronze module, which we have started yesterday. You can do the installation, as in this very first guidance. If you already did it, you can upload your previous certificate here, and then you don't need to do the other quizzes anymore. You can do them if you want, but you don't need to. And then you will see some quizzes here, 1.1 through 1.5. There will be 1 or 2 quizzes after each lecture, and they help you in your learning. Additionally, if you score at least 50% in each quiz, that is 10 points in each of these, and 70% overall, 70 points overall in this module, you will earn the certificate. There are also some more exercises to help you in Jupyter Notebooks. And all that guidance is here in this Get Started quiz. You see the link here to GitLab, and from there you can get started and download these exercises that are available for every lecture, and you can use them as much as you want for your own learning. Okay, I will quickly check the Discord questions, and then do you want to get your screen ready, Gibran?
Sure. Hello.
Wonderful. Yeah, there is a question about yesterday's recording. Indeed, we only shared the part of the launch, and the part from Gibran's lecture we will combine with 2 days lecture, so you will have the full lecture to do the quizzes. And yeah, and we will share more details on the Womanium badge and final certificate later. There are some questions about that. Oh, I don't know if any of the sessions would clash with the IBM Quantum Challenge starting tomorrow, Harry. We will have some very exciting stuff coming up, so stay tuned. When will the QBronze quizzes be available? Asked Julia. They are already they are made available one by one for the suitable ones after each lecture. As soon as you did your pre-programmed survey and assessment, then the first QBronze quizzes should be available to you now. Okay, let's get started, Gibran. How are you doing today?
Hello, excellent. Thank you very much, Malu. Much better than yesterday.
Happy to hear. Thank you, and thank you for being back. To everyone who didn't meet Gibran yesterday, Gibran Rashid is a board member at QWorld, and in addition, a professor in Karachi, Pakistan. He did his PhD in Calgary and in computer science and engineering, and has undergraduate degrees from Carnegie Mellon, and has meanwhile taught thousands and thousands of people in quantum programming, algorithms, and computing. And we are very excited to have you here, Gibran, to teach everyone right now.
Excellent. All right, time to get started. Thank you very much, Malu, for the wonderful introduction again. And hopefully today we'll be able to jump right into all the fun stuff. And I think many of the technical questions that were coming in during Olivia's session as well, hopefully some of them I'll be able to answer for you with kind of some technical details today. And for sure, some of them we'll be able to get to tomorrow. I see someone asking for Gibran's LinkedIn profile. Unfortunately, Gibran doesn't have a LinkedIn profile, so yeah, apologies. Anyhow, all right. So as I mentioned yesterday, to kind of connect back to where we left off, the QBronze workshop is kind of presenting quantum computing from a computer science perspective. So many of the questions you might have about quantum mechanics and quantum computing that come in from a physics perspective in terms of, say, what's the underlying physical process or whatnot, those details might be abstracted away, not to say that they're not important. For sure, they are even of more fundamental importance. But with the computer science approach, we are focusing on the algorithmic perspective, right? So we want to be able to identify, assuming the rule book of quantum mechanics, what can be done through a quantum computer. So that's essentially kind of the key goal from the computer science perspective, right? So we take quantum mechanics as a given, and the physicists give us kind of the rule book for quantum mechanics, pretty much like how we have the rule booklets of classical mechanics. And then what we want to know and what we want to do is, hey, what can we do with this rule book of quantum mechanics when we build a quantum computer. So towards that end, the first kind of part of the session today will identify how we really think about computation when we build it for classical computers. And then we'll transform that language to computation about quantum computing. And hopefully you'll be able to really see the nice technical connection between the two and how the mathematical machinery really just needs to be fine-tuned in a couple of places for us to go from classical computation to quantum computation. And so it's really insightful in the sense that we get a better understanding of what's the key distinction between these two perspectives. So towards that end now, so let's say we've got a physical system, and I want to abstract away from all the physical details of that system, apart from the fact that, let's say, I want to be able to identify, hey, how many unique states can that system be in, right? And so from a classical computer science perspective, obviously what you're trying to get at is, hey, I'm thinking about representing two unique levels of a system or two unique states, which we identify as a classical bit. It does not need to be a bit as well, right? So anyone who starts off computer science, was interested in computer science early on, has at some point a question, hey, why do we build classical computers using only classical bits? Why not have a 3-level system or a 4-level system? We'll get towards that in slightly as well. But to begin with, what we are saying is, hey, if we have a physical device, we don't worry about the physical details. Is it a photon? Is it an electron? Is it some other kind of physical system? For now, we don't care. All that we care about is, hey, it allows us to represent or identify some unique finite number. Everything that we will pretty much do in this workshop will be about finite stuff. And obviously, it should be non-empty because we should have some stuff in there, set of states. And so now there's nothing special about what are the symbols you associate with those set of states, right? So the usual language that a computer scientist might use is to say, I have an alphabet. So the unique set of states, a computer scientist would call them as an alphabet, that these are the symbols, the unique primitive symbols that I will work with. So in the bit binary case, I would say, hey, I've got a 2-level system and I identify them as, excuse me, zeros and ones. So a single 0 symbol and a single symbol for 1, but there's nothing special about them. I could have a happy face and a frowny face. Obviously harder to draw, but that works as 2 symbols as well. So all that I'm identifying to begin with is that I have a physical system that can be in some number of states. And I have a unique symbol associated with each of those states. So for example, I could literally have A, B, C, D as well, alpha, gamma, delta, or whatever. So moving forward, pretty much we'll fix our alphabet to be 0, 1, the set of states to be 0, 1. Right? So this is essentially then us linking the motivation kind of for doing this abstraction then is they're figuring out how to represent information using this physical system X, right? And as soon as I've represented information or stored information in this physical system, the very next thing I would be interested in is transforming that information or doing some computation on that information, right? So one simple way to think about computation on a single bit is just this kind of Boolean function. So I'm thinking about a function, it's Boolean if it takes as input a single bit and it outputs a single bit as well, right? So just based on this notation, how many functions do you think exist that map a single bit to a single bit? How many unique mappings can I have of this form? Kind of the table already hopefully gives it away. Excellent. So I've got 2 and a 4. So 4 again, 4, excellent. 4 is 4 wins by majority. 2 perhaps is the answer because people are disregarding the trivial classical cases where you've got constants. So, right, so the way we can fill in this table, imagine I've got my single bit represented here by small x. It has 2 possible values, 0, 1. And now each of the column headings over here are identifying the 4 unique functions I can have for that single bit. And obviously we can verify that these will then take the form. Well, I could have the constant function that always outputs 0. I could have the identity function. I could have the negation function. And I could have the constant always output 1 function. Right? So these are my 4 functions. that exist for mapping a single bit to a single bit. And, so for people who answer 2, perhaps you were thinking, well, these are trivial, always after 0, always after 1. So these are kind of the two interesting functions. Even between them, one is just the identity. So the really non-trivial computation that you're doing is this negation or flip by this function, right? So nice. So that means we, in some sense, encapsulated deterministic computation over a single bit, right? Now, how would we generalize that? Well, to begin with, easy computation that I'm sure all of us have some point thought about. If I've got n bits, Shamrita is already kind of answering a question that I didn't even ask. If I have n bits, how many different possibilities are there? There are 2 to the n possibilities. Excellent, right? So for example, if I have 2 devices, let's say x1 and x2, the way I might represent them is by saying, hey, rather than just a sigma, I have something called sigma 2, and that will be all the 4 possibilities. Note now, I'm not representing the 4, I'm not representing the functions anymore now. I'm still going back to representing the unique set of states I could have if I had 2 physical devices, each of them taking 2 possible values, right? So I just write down the 4 possible binary strings that exist of length 2, and as people are already familiar over here in the chat, sigma n, that would represent or would have size 2 to the n number of possibilities, right? So if I have n physical systems, each of them having 2 possible values, simple counting argument, 1 bucket, 2 buckets, 3 buckets, n buckets, each of them have 2 possible values. I multiply them out together to get 2 to the n number of possibilities, right? So if I have n bits or n physical systems that can take 2 possible values, then I have 2 to the n different possibilities. I can represent 2 to the n different unique states in some sense. Now, how about we connect it to the second part of what we did earlier? What about the number of possible functions I could have over this n bits? Right, so we've got 2 to the n possibilities for different possible states of n bits. But now if I wanted to do a computation over these n bits, what about a function that will now map these n bits? And for simplicity's sake, I'm not mapping it to n bits now, like we did in the previous case. I'm thinking of it as just a Boolean function, which in this case now is mapping n bits as input to a single output bit, which just takes a value 0, 1. Right. So I assume the first answer is n. With it is saying 2 to the 2 to the n. Arshit is saying same as before. So you don't need to send a direct message in Zoom chat. You could send it for everyone. When Arshit was saying same as before, I'm not sure what the before answer was here. But now, so for sure there should be a dependency on n, right? I'm asking about n bits as input, so the number of possibilities should depend on n. Most of the answers are of the form 2 to the n. There was one answer that was 2 to the 2 to the n, 4n. Can't get the question. So the question is, in the previous case of just a single bit, we identified that there are 4 unique functions that map a single bit to a single bit. Now we identified that if I have n possible bits, how many different mappings will exist, unique mappings that map n possible bits as inputs to a single bit as outputs? How many such computations, how many such functions exist? 2 to the power n plus 1, 2 to the n, right? So there's a bit more variation now in the different answers that you're getting. And we can easily kind of verify quickly that if you apply the same reasoning as before, you get an answer that looks similar as before, but it's not the same. So what do we do? Well, what are the number of different possible inputs I can have now? Well, I know already it's 2 to the n. Well, I can write them down in a table where the 2 to the n values go from all 0 string to the all 1 string. I've already verified that this will be 2 to the n number of possibilities. So this table has 2 to the n different rows. Now if I want to fix my function, this function will actually be fixing this entire column, right? So if I fix this entire column with 0, 1 entries, then I've fixed one particular function. Agreed? Right, so if I say, hey, here's 0, here's 0, here's 1, here's 1, and so on and so forth, for all the 2 to the n possibilities in the rows. Then I have fixed one particular function, the kind of Boolean function that I'm interested in. Agree? So people are still giving the answer, but like everyone, okay, yeah, all right, good. Agreed. So now there are 2 to the, just like there were n buckets over here, there are 2 to the n number of buckets or 2 to the n number of rows in here. So this bucket has 2 possibilities, this bucket has 2 possibilities, and so on and so forth. So it's 2 times 2 times 2 all the way till the bottom row, last row. So I get 2 to the 2 to the small n. So what's very nice and interesting over here, it's not just 2 to the 2 times n, but it's rather kind of a super exponential. So it's 2 to the 2 to the n. And so that's kind of very nice, right? That so no, 2 to the 2 to the n is not the same as 2 to the n. Yeah, if you can make it capital N, then that's fine. If you make 2 to the small n equal to capital N, then for sure you can write this as 2 to the capital N. So what's to take away here? It's interesting that the space of functions or space of computations that could exist for information or input size of size 2 to the n is again kind of exponentially increasing. It's 2 to the 2 to the n. And so in terms of looking for different algorithms, looking for different kind of machine learning classification classifiers as well, we identified this now that this really is going to be a really, really hard problem, because if you've got n possible inputs to begin with, the number of different possibilities are not just exponentially large, they're super exponentially large. And so this really is a difficult problem in terms of figuring out, hey, what's a nice algorithm that maps this input to this output? What is a nice classifier to learn a certain classifier for kind of input? So both machine learning, algorithm design are doing kind of stuff that's really, really difficult. Sure. So very quickly, we identify that in order to fix a Boolean function that maps n possible bits to a single output bit, what I'll need to do is to fix this entire column of entries to a single 0 or 1 for each row. Very much kind of like how I figured out, well, how do I identify the n different possibilities for n bits? Here I'm identifying what are the 2 to the n different possibilities for each entry in this row. So I probably stepped away from my device, so hopefully the voice is clearer now. Let me know if it's still not clear. So what I'm doing is I'm trying to fix each single bit in this row, and there are 2 to the n possible rows, right? And each bit has 2 possible values. So it's 2 times 2 times 2. How many times? It's 2 to the n number of times. And so that's why I get 2 to the small n or 2 to the capital N. So just to kind of take away from this, again, that the number of possible computations. So think of F as a computation we would be interested in. The number of computations you could do, numbers of algorithms that you can design really blows up. And so, we already get kind of an idea that thinking about computation, thinking about maps in where we're interested in, hey, how does this information map to just a yes or no answer? The answer that we were interested in over here was not a complicated answer, right? We were just saying, hey, for each input, give me an output which is just a yes or no. And even though that might seem limiting, most problems can be reduced to such a decision problem. So computer scientists usually love to work on problems that they call decision problems, and it's possible to really map nearly all problems to this structure, which initially might not be obvious because you're like, hey, my problem is an optimization problem, which is an optimal value of 3.274 or 191.2 or whatever. How does that map to a single decision 0 or 1? And hopefully as we go along, that will become clear in terms of how we can do that mapping. Good. So in some sense, if we have got perfect information about my physical system, so let's kind of quickly put on our like pseudo-physicist cap, and like if we had perfect information, perfect knowledge about my physical system, then in terms of characterizing the kind of computations I could do with it, in some sense this slide kind of packages it up nicely. There's no error, there's no probability, there's no noise. And so I have clearly figured out, well, at least in terms of counting, how many different possible computations can exist and what's my amount of information. However, obviously, the real world is not so simple. It's not going to be deterministic, perhaps. I won't have complete information. And so we are interested in what if I have incomplete information about the physical system that I'm working with, right? And so when I have incomplete information about the system I'm working with, what's the commonly used mathematical tool that we bring in? You already referred to it last time. I already mentioned it as well. What's kind of a nice mathematical tool that we use to model uncertainty or incomplete information about any kind of piece of system or, yeah, excellent, probability, right? So that's exactly what comes into play. So I will use probability to represent the fact, and through probability I get statistics, yeah. I will use probability to represent my lack of information or knowledge about the physical system. So I don't know, so I flipped a coin, I don't know the bias of the coin, it would be some probability P, so I know with some probability P it comes up head, and 1 minus P comes up tails, and so the nice little world of 0 and 1 is replaced now by kind of this number between 0 and 1, right? So if I flip a coin or if I have a physical device, it's not just a coin, and I'm not sure whether that physical device is in the state 0 or is in the state 1, I can only associate some level of certainty or some level of probability with it. So I'll get some thing of the form where I will say, hey, the best thing I can say is that the probability with which the state of the system X is 0 is, let's say, probability P. And if it's a two-level system, then automatically for the system to be in state 1, the probability becomes 1 minus P. So I've got kind of these two numbers. For sure, just the parameter P is enough. But it's nice to represent them together as a vector as well, right? So we usually would take this P and 1 minus P and write them out together, maybe even give them its own name. Hey, this is a vector, maybe with a hat on it or whatever notation you prefer for probabilities or vectors. And implicitly, we've got kind of an index of this vector as well, right? That this P represents, let's say, the physical system to be in state 0, and this for the physical system to be in state 1, or that the state of the coin was head, or the state of the coin was tails, or whatever else alphabet that I was using to represent the two unique states, right? So yeah, we are getting started with probability in this case, in this session, but we will end up with identifying the corresponding mathematical structure for quantum computing as well. But the initial part, definitely Mohammed is going to be about classical probability and operators. All righty. Now, one kind of nice thing to note over here, and just make a mental note of this, we'll come back to it when we come to kind of quantum systems and representing quantum information. That is, whenever we look, you won't give a second thought about looking at a classical coin flip, apart from, well, realizing what the result of the coin flip was. So let's say if I flipped a coin, and now I look at that physical device X, right, which could have been a coin, or could have been something else, the light switch that I used or whatever. Whenever I'm looking at this coin or the switch, I will not actually see the vector V. I will not even see the probability P, and obviously also not 1 minus P. And it almost might seem like a trivial thing for me to state over here. That obviously all that I will see is what? I will see exactly the labels in some sense that associate with the states of that system. Right? So somehow I could be able to say that if the states of the system, again, we go back to those deterministic symbols that we had identified from that alphabet, I will just see or observe the states symbol with the corresponding probability V sub sigma, right? So in this case, let's say I will see head with probability V sub H, let's say, which is P, and V sub T, which would be 1 minus P. So the operational or empirical output of a probabilistic observation of this probabilistic system is not going to be either the vector V itself or the probability P, but rather just one of the symbols that we associated with the system. And we'll see that that's something that obviously happens in the quantum case as well, but sometimes can lead to a little bit of confusion, which we'll get to. Multi-level systems, we're about to get to that nail soon, right? So how we represent, so you're asking multi-level, not multi-party. A multi-level would be, let's say, good. So if I have a 3-level system, right? So I could have x equal to 0, x equal to 1, and x equal to 2. Well, then I could say, hey, this has probability P1, this has probability P2, and then because of normalization, obviously, this would be 1 minus P1 minus P2. Right? So you'll have a bunch of probabilities, and essentially what you'll identify is that the entire vector has to be a probability vector, right? And you can generalize this to any dimension n. I shouldn't use n because already used that for the number of it. All righty, any questions here? All right. So obviously then, how do we transform this information? Just like we were looking at transforming classical information when it was deterministic. Well, let's quickly see an example. If I have this vector p1 minus p, given that we know matrix algebra, then we already are familiar with that. Here there's something called matrix vector multiplication. So I could take the vector p and 1 minus p and multiply it with matrices to get new vectors. How do we calculate these probabilities in classical systems? So I assume right now that we are told or we are able to identify what these probabilities are. Some examples in the Jupyter notebooks will lead you through exercises where we actually exactly gain statistical information about how confident we are, what are the probabilities. But for now, let's just say we know what the probabilities are for the specific questions that we're doing. Now, going back to just this quick example that we're doing, just to get an idea of how do we do transformations for classical information, which is incomplete, i.e. we are interested in how we map vectors to vectors. Well, we will multiply them with matrices. One possible matrix, for example, could have been 0, 1, 1, 0. Very quickly, what would be the output in this case? If I were to multiply this matrix with the vector p1 minus p, hash note. All right, so very quickly, so Akash asked the quick explanation again of the note. So very briefly, the observation that we are just making, a trivial observation in some sense, that when I look at the coin that I just flipped, so let's say the physical system X that I was interested in was a coin. I flipped it. Obviously, when I flip a coin, I don't see the probability P, right? I don't see the vector V as well. The vector V is really a mathematical construction that we have to represent information about this object. All that we see are again the state symbols that we had associated with heads and tails. Right? So I would say, hey, the coin came up heads, or the coin came up tails, the switch is on or the switch is off. So whatever were the symbols we associated with those two kind of different unique states, that's the output, right? No, this is for classical systems, right? We haven't started anything about quantum yet, but we'll see there will be something very similar happening there as well, obviously. And now going to the example, people already shouting out in the chat that obviously this will be 1 minus pp, and in some sense you've verified that this is the negation operation that we already see in the deterministic case. This is that same operation now represented as a matrix. Now, a very nice kind of thing to kind of link also is, well, how do I think about these 4 entries in terms of what they are doing? I already kind of verified this explicit example, but then you kind of already see what's happening in this case. So if had these 2 entries been 1, 1, and the anti-diagonal entries been 0, 0, then this would have been the identity matrix, right? So in this case, this matrix signifies an operation that we are doing on the physical system, just like the Boolean functions f was signifying a deterministic operation that we're doing. In this case, this again still is a deterministic operation that we do on the system, right? Which leads us to, well, what are the 4 possible deterministic operations represented as matrices? Let's quickly write them out. So the 4 deterministic operations that we had identified previously on classical bits represented as matrices could be written down as, let's say, always output 0, always output 1, identity, and the one that we just verified in the previous slide, negation. Right, so the 4 Boolean functions that we identified, Tego, where did I lose you? Matrix or all matrices, right? So in this case, these 4 matrices are the deterministic matrices that represent the 4 Boolean functions that we identified in the first slide for the deterministic Boolean functions, right? So these 4 Boolean functions that were mapping a single bit to a single bit, we can verify that these 4 matrices perform exactly that transformation, but now over kind of probability vectors rather than just a single bit as input. So I get my ability to transform deterministically my probability vectors into other probability vectors, right? So I see some messages where people kind of are finding it hard to follow along. So perhaps one of the key things that's happening over here is that I'm assuming people can follow the matrix algebra in terms of just multiplying out matrices with vectors. If that's the case, I strongly recommend using a matrix algebra reference. The Jupyter notebooks already do have a brief background in kind of matrices and vectors. So you definitely want to review those in order to follow what will happen for kind of pretty much most of the session moving forward. And that's really the key thing to observe, right? That all of this is really just talking about transformations, Boolean transformations represented in terms of matrix algebra. Right? We haven't done anything quantum yet. All that we are talking about is classical transformations on classical information. Right? Right, and so a good exercise for you after you work through it is to identify why these 4 vectors, these 4 matrices correspond to the 4 Boolean functions that we identified first. All right. Okay, but as one might argue, so apologies, I just assume that people have some matrix algebra background. I realize some of the people right now on Zoom don't have it, so please follow along via the Jupyter notebooks first, and then hopefully if you come back to the recorded video for this, it would make sense. But unfortunately, I won't be able to go back and do all of matrix algebra here as well. Alrighty. A1 and A2 are same, and A0, A1. No, A0 and A1 are not the same, right? So a quick way to verify it is basically just multiplying out these matrices with specific probability vectors and see that they are not the same. In one case, this is always output 0, and let's say this is always output 1, assuming you make the corresponding indices, this being 0 and let's say this being 1, and vice versa. All right, so why did I select these 4? These 4 are just, these 4 matrices are the matrix version of the 4 Boolean functions that we had identified in the first slide. However, you can definitely think about what would be the probabilistic version of these transformations. Obviously, there will be more, right? They won't be just these 4 transformations. Just like in the classical case, I had 0 and 1. That was deterministic information. However, when you do probabilistic transformations, you're allowed to take a mixture of, let's say, these 4 deterministic transformations. And so in this case, to get a probabilistic operation, right, you can say, hey, I will take a weighted combination of these 4 matrices. And these matrices indices run from 0 to 3, right? So this is me saying really just P0, A0, plus P1, A1, plus P2, A2, and P3, A3. Now the P over here is not the probability that we had previously for the 2-level system. Rather, the P over here is representing the probability with which the gate, if you prefer to call it, or the matrix or the transformation A0 is applied P1 is a probability with which A1 is applied, and so on and so forth. So operationally, automatically, it kind of makes sense to think about this, that if each one of these four matrices were deterministic transformations, then the probabilistic combination of these four transformations is also going to be a valid classical transformation. All right. So yeah, these slides over here will be posted, so don't worry about that. The link will be posted on Discord. So for example, let's quickly verify that if I were to choose just half A2 and half A3, what would be the corresponding transformation that I would get? What's the new resulting matrix? So right now we don't have to worry about calculating eigenvalues or eigenvectors. So these half are the probabilities, right? And so I fixed P0 and P1 to be 0, P2 and P3 to be half to get this kind of combination over here. And so what would be with this combination? You will get, very good, you're getting the answers. It's just basically, so you see the matrices now end up looking a bit more interesting than just 1, 0 entries. And so the entries are, in fact, as we'll quickly see, each entry in these matrices can be thought of as a probability itself. Right? It will represent the transition probability if my state is in, let's say, whatever is the index of the column, to transition to whatever is the index of, let's say, this row or this row. All right. In fact, this matrix, in some sense, you could also think of it as, let's say, a classical coin flip, where the bias is exactly half, right? So if you apply F to any matrix P1 minus P, what comes out? Right, so all half entries, very good. Many people give the right answer. Now, what about applying F to just the probability vector P1 minus P? It's the next state of the system, but now in this case, what is the next state of the system? So if you just do the matrix vector multiplication, you'll verify that this just gives us half 1, 1. And that's kind of the reason for calling it the coin flip kind of matrix, right? Because no matter what the input system was, no matter with what probability I started with a head or a tail, let's say, the output is always going to be a coin, a head or a tail with probability half each. So it's like simulating a perfect coin flip with no bias, right? So it's exactly a fair coin flip, right? So we've seen how to take deterministic transformations and through them build probabilistic transformations, but there's a nicer way to characterize the space of transformation as well, which we'll try to build up to. But before doing that, let's kind of do one more example that perhaps motivates why kind of doing all this mathematical machinery has some payoff, has some benefit, right? So let's take this slightly more interesting, non-trivial protocol. So this is kind of a two-level operation. So we assume we have got a coin, and that coin, we a priori don't know what's the probability of it to be head and tails. And I'm assuming in this case that the first index is referring to the tails, and the second index is referring to the coin being head. So I've got a coin which will, when flipped, come up tails with probability P, and will come up heads with probability Q. So that's kind of the result of the first coin flip, if you flip this specific coin. Now, the protocol that I will follow is that after flipping the coin first once, I will flip it again, and I will follow these rules for whether or not I'm flipping it again. If the result of the first coin flip is a head, I will flip the coin again. All right, so I flipped the coin once. With probability P, it came up tails, and probability Q, it came up heads. And now I observe that if it indeed did come up head in this first coin flip, then I will just flip the coin again. And in the second case, if we get a tail, then actually I will not flip the coin, but rather just deterministically kind of turn it over such that the coin state becomes a head. Right? So there's kind of this two-level procedure that I'm implementing. For sure, you could individually work out the probabilities of how this protocol gives you heads, tails, heads, or whatnot. But we'd like to kind of nicely characterize this entire protocol, let's say, as one single transformation. And so what we'd like to think of is, can I characterize this transformation, this protocol, as kind of this probabilistic operation that we thought of in the last time? So let's say as kind of a convention over here, that the first index is for tails, the second index is for heads. Similarly for the row, the first index is for tails, the second index is for head. And now again, we'll reiterate the convention that this tail versus, let's say, this head. What's the understanding of the entry that goes in this index? Well, it corresponds to exactly the probability with which, if my system is currently in the state tails, what's the probability with which it will transition to state head? All right. So let's kind of make a note of this. So this, and then given this entry over here is given that my current state is tails, given by here, this entry gives the probability to transition to heads. Why? Because that's the index of the row over here. Alrighty. So now let's just work through it. We got some people asking about Hadamard. Kind of give me kind of till the end of the session. We'll get to Hadamard as well, whether or not this is like applying Hadamard from the previous case. Alrighty. So what I'd like to do now is to take this protocol over here that's listed here and use it to fill in this matrix over here. I see some of the people have already shouted out answers. That's great. Not all of them necessarily correct. So for sure, let's take the simpler case, right? So if we get a tail, so I know that I fixed this column, then the coin, we just deterministically flip over to make it a head. So in this case, for sure, the new state is a head. So this will be a 1 and this will be 0. Now note the way I have identified the meaning of this transition over here automatically gives us this intuition that each column in this matrix can now itself be thought of as a probability vector. And that's a very nice intuition to have, right? Each column of this matrix, if this is really going to be a valid classical transformation, is really going to be a probability vector in of itself. Because this column over here identified exactly what we do in this specific situation, which itself identifies a probabilistic process. Similarly over here, if we get a head, we flip again. Well, if we are flipping again this coin, what's the probability it comes up head? What's the probability it comes up tails? And so that's where perhaps some of the participants got confused. In that case, note, we did not say that we have a pair coin. So it won't necessarily come up half-half. It will come up tails with probability P, and it will come up heads with probability Q. Right? So that's why these entries over here will be P and Q. So apologies if you got confused just from the previous example where we looked at F as this half-half, all half entry matrix. But here this is not the F matrix that we're making. It's really just this other transformation corresponding to the protocol that we have over here. Right? Hopefully it makes sense. Some people, yes, already saying it makes sense. Good. Hopefully it also clear why the second column is not half-half. Alrighty, so what's the big payoff? Well, if we did this, now figuring out the new probabilities of, well, what's the probability with which after this protocol is done, the coin is in state head or state tails, I really just need to do this matrix vector multiplication to get a new vector out, which I'll let you verify, ends up being PQ and P plus Q square. So totally not kind of trivial or obvious probabilities to begin with, right? Excuse me. Right, so you've got these two different probabilities, but they precisely identify with what probability will the state of the system be head or state of the system be tails after performing these transformations. So not the new matrix, but the new probability vector is this vector. And this again connects us to a nice way of thinking about these classical transformations. It's that all matrices will represent valid classical transformations that will map probability vectors to probability vectors, right? Because the outputs after the transformation have to be a probability vector as well in order to make sense, right? And the only way that will happen is if the columns of each of these matrices are probability vectors as well. So yeah, sure. So I'll repeat. The way to think about these transformations, what is the space of classical transformations? It's the set of matrices that will map probability vectors to probability vectors. Well, obviously, because if the output is not a probability vector, then it's not really, representing probabilistic information the way we defined it to begin with. We said that, if you've got probabilistic information, then the way to represent it is via probability vector. So if I apply a gate, if I apply a transformation, if I do some kind of information processing protocol, and I'm keeping all the information in some sense contained, right? So there's no loss of information to the environment kind of thingy. So then all of this information is still contained in my vector. So that means the classical matrix has to transform a probability vector to another probability vector, and that gives rise to a nice characterizations for which we can say in general, any matrix is a valid classical transformation if two things are satisfied, which is essentially really just one thing. Requirement 1, all the entries in the matrix are greater than or equal to 0. And 2, sum of entries in a column is 1. In other words, they have a nice name for these kind of matrices. You call all these matrices stochastic matrices. There's much more to it. There are exercises for it in your Jupyter notebooks that you can work through to get kind of more intuition about them. But you note now how this corresponds to exactly the intuition that we had given this labeling, that what we end up having if we satisfy these two requirements is that each column is really just a probability vector. Can I explain the head column again? I'm not sure which part of the head column you're referring to. Yes, Shastri. Right. To get the probability, is there such a thing as negative probability? There are a bunch of nice kind of exploratory papers that look at negative probability. For our purpose, we won't kind of work with negative probability, but for sure we'll perhaps take just as good a version in terms of talking about quantum amplitudes. We'll be getting to them soon, hopefully. The column part, how we put P and Q. Right, so quick verification of why we have P and Q over here, because the protocol said if we get a head, so we know we have fixed our column label to be a head, we will flip the coin again. Now, flipping the coin again, what's the probability of getting a head and a tail of a single coin flip? Well, that was given as this first piece of information, right? So this is a coin that whenever we flip it once, the probability we come up tails is P and the probability we come up heads is Q. So we really just need to plug in that vector over here in here, right? Right. So Mohammed, so these are two individual probability vectors, right? So when you say it's a four-membered vector, sure, yeah. So there are cases when you can think of vectorizing this matrix as a vector, but we don't necessarily need to get into that right now. But yeah, it makes sense to think about it that way if you want to. All right. Okay. So for sure, this might be too much if you aren't familiar with matrix vector stuff. So hopefully you can kind of come back to it later as well. where the recordings, post your questions on Discord, and hopefully we can do that as well. So I'll try to move on, and then if there are still questions about this particular slide, I can take them on Discord. You can post them in the QBronze program module session in Discord. Alrighty. As someone asked about higher levels, well, let's go the other way around, like we did for deterministic systems. What if I have more kind of physical devices, but each of those devices are devices regarding which I have incomplete information, right? So I could have coin X1 and I could have coin X2, and both of them may actually follow a different probability vector, right? So this one might be PQ, this one might be RS. How do I combine these two probability vectors? Here's something that probably very few of you might have seen, but it's doing something that intuitively we've always been doing when you got introduced to probability and doing sample spaces and calculation of probabilities in sample spaces. That's all that we are doing here, Nigar. So all that we are doing is calculating the probabilities of the next state of the classical system. Awesome. Alrighty. So how do I combine the joint information of these two points, of these two physical systems? Well, we do something called a tensor product. You take the first vector, you write down this X inside a circle to represent a tensor product. You write down this vector, and now the way you combine it is really you take just all the possible combinations. So you get PR, you get PS, you get QR, and you get QS. Well, why these four numbers and why this ordering? So think about it this way. If this was tails, this was head, this was tails, this was head, and when I'm combining these two different physical coins being flipped, and I want to look at the sample space of the events that will happen, well, it could be, well, what's the probability the first coin came up heads and the second coin came up tails, and vice versa, or both of them came up tails, both of them came up heads. There are four possibilities, right? Exactly using the same kind of counting argument that we've seen previously. So the way you could think about these four probabilities in this vector are, and indeed these will be probabilities because these are just probabilities being multiplied out together. And the index of this, excuse me, vector could be thought of as being labeled as tails, 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 heads, heads, tails, head, head. So all that we've done via this tensor product is combined the four different probabilities of the bigger sample space and written them down in my probability vector, right? And note how the dimension of this vector has increased. If initially these two initial vectors were of size 2, then the new vector is of size 4, of dimension 4. Now, if I had n such vectors, the dimension of the vector, the resulting vector will be 2 to the n, right? So here's a nice kind of, again, mental note. This increase in the number of possibilities of the vector to be exponential is something that's already happening for classical probability vectors as well. So it's nothing kind of unique to quantum, which we'll see once we get there as well. So this exponential increase in the dimension of the probability vector when you combine individual probability vectors is something totally, completely classical, right? It's already happening here in the classical case as well when we use the tensor product to combine classical probability vectors. In fact, it's exactly this operation that we use to combine quantum vectors as well. So there's nothing special or uniquely quantum about joining systems using the tensor product between classical versus quantum. The dimension in both cases is exactly the same, the size of the dimension in this case, right? It's 2 to the n in this case, right? Not the 2 to the 2 to the n, but it's just 2 to the n. Now, one interesting observation to make, perhaps more non-trivial note, even though, so this implication was going kind of, if you've got two vectors, here is the construction to combine it to get a bigger vector, right? However, not all four-dimensional probability vectors can be written as a tensor product. Of two-dimensional probability vectors, like we did above. And that's, again, perhaps from the probability part, it's something obvious, but you see that I can write down this vector. People throwing out entanglement already. At the moment, there's nothing entangling over here. All is classical, right? So I have half 1, 0, 0, 1. This is a classical probability vector. There's no notion of quantum entanglement for us at the moment. All that this above note is saying is that this vector cannot be written as a tensor product of PQ tensor RS, which is the vector as we wrote PR, PS, QR, QS. And I welcome all of you who haven't thought about this before to try to verify this, right? So you just observe that, hey, if I note that these two entries have to be 0, well, if these two entries have to be 0, that means these two entries have to be 0. That means either P or S is 0 or Q or R is 0, right? So either P or S has to be 0 or Q or R, one of them has to be 0. But then when you follow through with the logical implications, you require these to be half as well, and that just doesn't work out, right? So you verify that indeed this vector cannot be written as a tensor product of these vectors. Now, mathematically, coming in from probability, perhaps, especially if you combine that with excuse me, the way you calculate probability in sample spaces, it might not seem that weird, right? So all that we are saying is that these two random variables corresponding to the probability vectors that we had were independent. This is, again, so I see lots of comments in Discord about entanglement and Bell states. Here we are not talking about entanglement at all. This is completely classical. And I'll try to say a bit more today and tomorrow again about this. This is not a Bell state. This is just a classically perfectly correlated system. Because it's correlated, you can, the two random variables are not independent. Hence, you cannot write them down as probability of x1 times probability of x2. So that's like it's one of the more important subtle takeaways from this discussion, that this issue of two random variables being dependent or independent is something, again, obviously, that happens in classical probability as well. So the fact that you can end up with larger probability vectors that cannot be decomposed into smaller probability vectors, again, is something that happens in classical probability. It's not uniquely quantum. And we'll talk about more when we get to it, is what exactly is the distinction between larger quantum vectors that are said to be entangled, whatever that is, and classical vectors which are correlated, right? So the correlation over here refers to the fact that in some sense, when you look at the system, either it's always going to be tails, tails, or head, heads, with probability half exactly. So that's the correlation between the two, right? Right, so someone asked whether you can think of the coins as being glued together. So that I'll come to that point exactly when we do the quantum part, whether or not the two coins are glued together. In some sense, if you imagine doing two independent coin flips, then you do not expect them to be correlated, right? Because, well, they are independent. But the fact that two coin flips end up behaving in a correlated way means that somehow the two physical processes are connected. How they are connected, that's something that we'll get into later if time permits. But the issue is that there has to be some source of that correlation, how that correlation is being generated. We won't worry about how it is being generated at the moment, and just kind of just make this observation that indeed there is correlation here. And this correlation, though, has nothing to do with quantum. It's just referring to classical correlation. Is PR equals to RP? Is order important? Good question, Prithviraja. I recommend you kind of verify that, right? So to take two kind of probability vectors and take a tensor product and see whether they end up being the same thing or not, right? So take probability vector 1 and vector 2, combine the two together. Is that the same system or not? So the most approaches that we're familiar with are kind of statistical in terms of finding out whether or not two probabilities or whether a given probability vector has correlation or not. There are statistical tests. That's a question that people deal with in terms of verifying whether a certain quantum process was actually genuinely quantum as well. It's a great discussion to have in on Discord. I might not be able to get to it within this discussion, within these two sessions. Alrighty. All right, so hopefully everyone is kind of okay with this note. Please keep this in mind, and hopefully we'll be able to kind of review it when we come to it. All right, just like we could define a combination of multiple probability vectors, similarly, we could also combine multiple transformations as well. And it would happen as one might emerge in a similar way if I have transformation A on the first vector, and if I have transformation B on the second vector. And let's say these are given by A1, A2, A3, A4 for A, and B1, B2, B3, B4 for B. How do I combine these two matrices together? Well, first of all, without even doing the computation, what's the size you would want for A tensor B, given that A and B both are 2 by 2 matrices? 4 by 4, 4 by 4, yes, most answers 4 by 4. Total number of entries, obviously 16. Good, very good. Nice, people are following along. Kronecker product for tensor. Not 16 by 16, 4 by 4. Right, why 4 by 4? Because we just verified that when we combine two two-dimensional probability vectors, the resulting vector is a four-dimensional vector. So it pretty much follows that, the transformation then I should be applying on the corresponding physical vector for this physical system should be a 4 by 4 transformation. And indeed, that's exactly what the definition gave us. One nice short form way of writing it is, hey, this is just the scalar A1 multiplied with entire matrix P, scalar A2 multiplied with entire matrix P. You get the idea. Right, so that's your 4 by 4 matrix for getting your combined transformation. Note, even though the way I've written it, one might be thrown off that, hey, this is 2 by 2, but this is really a 4 by 4 matrix, and each B itself is a 2 by 2 matrix. Good. So we automatically get the notion that we've got larger transformations to correspond to the same dimension as the probability vectors that they will be applied to. Now, is the combined transformation first applying A and then B? Actually, the order in some sense wouldn't really matter because because you're applying it on different systems, right? And because it's a tensor product, you can kind of write them out separately. It's kind of an independent transformation. A is getting applied on system X1, B is getting applied on system X2, and because they can be written as a tensor product, they are really independent transformations, and so you can indeed do them independently. Excellent kind of noting. However, if there was a transformation that you could not, if there was a 4 by 4 transformation that you could not decompose into smaller 2 by 2, 2 by 2 transformations, then we would get the notion similar to as we did in the previous case in terms of the probability vector, that hey, this 4 by 4 transformation, if it cannot be decomposed into the smaller transformation of 2 by 2 matrices, then it's not an independent transformation, and it's kind of something that requires the two systems to be combined in some way. And so there, the order kind of then would be dictated by how the transformation is combined together. And we'll see exactly an example of that, which is this operation over here, which some of you who are already familiar with what we are doing over here have seen. So it won't be an 8 by 8 matrix, right? So if it's not a tensor product, so for example, just like over here, we said there are 4-dimensional vectors that cannot be written as the tensor product of two two-dimensional vectors. Similarly, there are 4-dimensional matrices, 4 by 4 dimensional matrices that cannot be written as a tensor product of two by 2 matrices. And one kind of very explicit practical example of that is the C0 matrix, which is also called the controlled, the C is for controlled, not matrices. So the not we already seen is the negation operation. The control here is referring to the fact that when we visually represent this operation, so first of all, what's happening over here? I've drawn a small circuit. Time travels left to right, as is the case for all classical computation or computation circuits that are usually drawn. I've got two bits coming in, X and Y. This filled in circle identifies a control operation, and this filled in refers to the fact that this is controlled. This is the control bit. And this part over here means that this is the bit on which the not operation will get applied. And very quickly, this just says apply not on second bit if first bit is 1. So in some sense, the first bit being 1 or the first bit being switched on means that the control has been switched on. If the control is 0, then the control is off and nothing happens. So you see how there's kind of a connection that's been built into this operation, that what happens on the second bit is being controlled by the value of the first bit. And so it suffices for us to understand what this operation does on the 4 basis vectors, the standard basis vectors, right? So what are the standard basis vectors for 4 dimension? Right, so they'll just be 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. Now it suffices for us to figure out what any operation does on the standard basis vectors to understand what it does on any other arbitrary vector, right? Because any vector, probabilistic vector, is just going to be a probabilistic combination of these 4 vectors, right? So very good. I should write that this is the first bit and this is the second bit. So if I were to try to build, and some of you have already given it an answer, but if you don't know the answer, let's quickly try to verify that. I want to come up with a 4x4 matrix that implements this operation. Let's figure out what this operation does directly on the standard basis vectors. Let's think of this matrix as n. If I apply n to the vector E00, well, what's E00? Well, that's this vector, E00. This is E01, this is E10, this is E11. Alrighty? So these are the 4 basis vectors. I am now trying to figure out what these basis vectors are transformed to under the operation n. So E00 is this vector, right? So what the 00 kind of in the index refers to the fact that it implies that the incoming value is 00. Well, what does the control not operation do? Because the control bit is 0, so the NOT gate doesn't get applied. So in this case, it acts like identity. E00 gets mapped to E00. And using the same reasoning for E01, because the control bit, the first bit, is still 0, nothing happens. I get the same vector as output. When the first bit is 1, what do you think will happen? Wait. I'm sorry. E11, some people gave the right matrix as well. Excellent. In this case, I get E11, and obviously in this case, I'll get E10. All right, so in some sense, I've completely characterized the matrix N via these 4 equations. And in some sense, what I can do is to write down these 4 vectors directly in this matrix, and I've got the full transformation as well. So I write down 1 0 0 0 0 1 0 0 0 0. What comes next? Excellent. 0 1 and then 0 0 1 0. Note that each of the columns over here is exactly the output column that we identified over here. That's one way to look at it. Another way to look at it is that this submatrix is kind of the identity matrix, because that's exactly the identity mapping over here. And over here, you've got the NOT gate, because this is exactly the NOT gate being applied on the second bit when the first bit is flipped or switched on, or the control bit is on. Another observation to identify, and that I leave you to kind of work out, that this 4x4 matrix that we have just identified indeed cannot be written as a tensor product of these two such matrices. Why? Because here these two are independent transformations with two individual bits, whereas this thing, as we've just seen, is not really an independent transformation, but it's really kind of a combined transformation. And the way we've combined it really depends on, well, whatever the construction of this operation was supposed to be. In this case, the logical construction was, if the first bit is 1, then apply a NOT gate on the second one. Right? Right. So Gaurav is requesting a break. We are pretty much done with the classical part of our conversation as well. So just give me a couple of minutes, and then we could take a 5-minute break. I hope that's okay with everyone. Right. I'll be able to get my coffee in as well, right? All right. So I know some people kind of, hey, where did this matrix come from? Let me quickly review that, leave you with a question as well, and then we'll take a 5-minute break. Hopefully everyone's okay with that. All right. Right. So where did this matrix come from? There are multiple ways to think about it, and each of them hopefully gives you a different input into this as well. One, well, people were able to verify these 4 equations. Hopefully, if not, just say, hey, this rule, if I implement it as kind of a condition on what this circuit or what this matrix is supposed to output, pretty much defines that, hey, the output of n applied to this vector will be this vector, and so on and so forth. Once I identify that, then you really have this observation that what I can really treat this matrix as vectors as is really just these 4 output vectors. You write down these 4 output vectors in order for, hey, 0, 0 gets mapped to this vector, 0, 1 gets mapped to this vector, 1, 0 gets mapped to the 1, 1 vector. So no, this is the 1, 1 vector, not the 1, 0 vector, and so on and so forth. Where's a standard basis dimension for? Because in this case, we are working on a dimension for, right? So we were thinking about operation on 2 bits, and we verified in the previous slide that the dimension for 2 bits will be 4-dimensional. Is this a probabilistic transformation? Good question. What do people think? Is the controls not a probabilistic transformation in of itself? No, all right, it's a deterministic transformation, right? Sure, the input might be probabilistic, but the operation itself is really a very deterministic one. And you can kind of see that by looking at this. You can see that by noting that each of the vectors over here in the transformation itself are deterministic vectors. Right, so there are multiple ways to take that. Again, another way to think of it is, rather than if, let's say we did not have these 4 equations, you could literally take this rule and directly construct the non-zero entries of this matrix. And the fact that we already know this characterization that for a transformation, a classical transformation, each column is a probability vector, and we know that I get a 1 entry in each column, then all the other entries automatically will have to be 0, right? So there are lots of nice ways to think about getting, and so that's kind of one of the nice things that attracted me to quantum computing as well before. So you have this mathematical stuff in front of you, and there will be so many different ways of approaching that math and getting something else out of it. You look at it kind of a CS perspective, you look at it as a physics thingy, you look at it from a philosophical perspective, a material science perspective. And so going back to the starting joke from yesterday, there are lots of takeaways that you can have depending on how you look at it. Right? Alrighty. So for the 5-minute break, I leave you with this exercise. You don't need to answer right now. I won't provide the answer during the session itself as well. It's a nice little trick. And so assume someone hands you a biased coin. You don't know the bias, right? So it's a coin. So really think of it as a physical thing, right? Your friend comes up to you, hands you a coin. You don't know the bias of the coin. You are guaranteed that it's not a fair coin. And it's also not a completely deterministic coin, i.e. it's not the kind that will always come up heads or to always come up tails. Now, the job for you is to figure out how you can simulate a fair coin using this biased coin. So come up with some kind of protocol that will allow you to simulate a fair coin flip using a protocol that you do, which may involve multiple flips if you like, or some other task that you may like. At the end of the day, you can write it down as a transformation. So what would be kind of the protocol that you would do where the input is a biased coin and the output is a fair coin flip? All right, and so we'll take a 5-minute break now, Hopefully, Malu, that's okay. And we'll start in, let's say, what would be, in my case, 9:40. So we'll have 20 minutes to get everyone up to speed on quantum information.
Yes, fantastic, and very well deserved to have a break. Let me see, there should also be a timer app, and then I can, okay, I turn it on. Can everyone see a timer in the back of my screen?
I can.
Okay, great. So then it is clear when the break will end. Feel free to take a break, everyone. In the meantime, Womanium team, please turn on your video if you're available for just some chatting and Q&A. And for those who don't need a break, then you can stay on, ask more questions, and have a chat with us. Sada is asking, is this session on YouTube live right now? Yes. Jasmine, can you please assist and share the link again on the Zoom chat and in the Discord chat? For everyone for whom it's going a little bit fast, no worries. This lecture will be posted on Canvas and Discord as soon as possible, hopefully today, otherwise tomorrow. It will also include yesterday's lecture, so you will have both parts combined and can then go on with the exercises and quizzes. Let me share what is coming up tomorrow. 1 second to share my screen. There we go. Tomorrow and Friday. Tomorrow, we have first a game session coming up, Quantum Odyssey, and then the next lecture and a tutorial on QBronze. In this tutorial, Claudia from QWorld, Claudia Zendeos Morales, will come to show you how to approach the exercises and how to actually program a quantum circuit and how to work with Qiskit. On Friday, we will have a keynote and a virtual lab tour in quantum computing at MIT, led by Will Oliver, professor at MIT, and Shantanu Jha. And then we will have the final QBronze lecture. Vardaan, could you share a bit more about this game, Quantum Odyssey, and also on Friday, Grover's algorithm? What is that and what is it useful for?
Sure. Yeah. Hey everyone, welcome back again, and I think you all deserve a 5-minute break. So I'll be very short in the description. You all should have received the link to download the game and install it in your local devices. It should be in your welcome email. It's Quarks Interactive, provides a free license for Quantum Odyssey to everyone participating in the Womanium program. So that's an amazing opportunity for everyone to try that game. If you are not a part of the Womanium program, otherwise you would have to purchase that license, and we do not want you to go through all that process. We are making that available for free for everyone, all the Womanium scholars, everyone who's participating in this program. Do go through this module as Maru is showing on the screen. Go through all the details, go through the team. Do make sure to like this and wish list this so that as soon as the updated version of this game comes, you are ready and you get all the updates. But apart from that, do download this game. It's an amazing opportunity. All the quantum stuff which you are going through the lectures, at least the fundamentals, you can also go through this game scenario, right? In a very interactive and fun manner. You can learn what entanglement is, what qubits are, what superposition is, all the zeros and ones you have been talking about in the QBronze lectures. I'm pretty sure you'll get a very good interactive and more visualized speed during this quantum Odyssey game. So this is completely on a self-paced stuff. There's no assessment for this game. You can do this on your own. You can find peers in the Discord chat and maybe schedule gaming sessions together, right? Just choose some slots during the day and compete against each other. Everything is possible. It's games, right? And if you do have any exciting news, perhaps you got a new high score or you're competing against yourselves, you want to share your snapshot, Discord is the way to go. So we'll be very happy to see any screenshots of that and your experience playing the game in the Discord chat as well.
Then on Friday, Vardaan, Grover's algorithm, what is that useful for?
Oh yeah, Grover's search algorithm, one of the capstone quantum algorithms. I'm sure many of the ones in the program who are already familiar with quantum algorithms. Grover's is one of the key algorithms one learns at the very beginning. So this is where a very fundamental algorithm which shows how you can use searching through a database much more quickly and efficiently using quantum stuff. I won't give you the spoilers just yet. I think you go through the Q-Bronze tutorial and you'll get a better understanding of what I mean. But the good thing and exciting thing over here is that Erica Sturm would be giving this lecture, and she was a participant last year. Not only was she a participant in the Romanian program, she graduated the program and now she is working as a QSL fellow. So all the QSL opportunities which I was talking about yesterday about the project and everything, Erica Sturm is one of the fellows who was selected to work with the Naval Nuclear Lab. Today she is working on one of the projects over there, and now she has been promoted to give a lecture to you guys on Q-Bronze, which is a huge achievement for her, and we as a Romanian team are very, very proud of her. And I think, yeah, you all deserve those kind of opportunities. So I'm very excited to welcome all of you to give lectures to next year onwards.
Then there was a question earlier in the session with Olivia Lanes asking, is there anyone working on quantum computing for optimization problems here? Stay tuned for this the next couple of weeks. We will dive into both gate-based models and quantum annealing. And then for the projects, this could be a potential project where you do the quantum optimization for climate applications or others. Then a question to you, Gibran, while starting everything. Someone asked what kind of research work is currently going on in quantum algorithms. Can you give some insight?
Sure. So as some of the questions that were asked in the earlier session as well regarding quantum advantage. And so that's something that came out of NISQ consideration. So the idea that a feasible large-scale quantum computer is perhaps some decades away, and people were interested in could we get some kind of interesting advantage, interesting benefit using quantum computers today with whatever kind of technical hardware we have available today. And so one of the big open kind of research areas today in quantum algorithms would be to identify and build algorithms that you could run on current hardware. And so that's really something non-trivial, right? So it's not just saying, hey, I've come up with an algorithm that works on this theoretical being that exists, which is a feasible large-scale quantum computer, and then Shor's algorithm obviously does that. But now what I'm really looking at is, hey, there are these limited computational devices with inherent kind of restrictions because of the noise level and whatnot. Could I still do some kind of computation on these limited devices where I get an advantage in terms of the amount of memory I use, in terms of the amount of time the algorithm takes, in terms of the amount of energy needed to run the algorithm, or in any other measure of resource that one would be interested in optimizing? Could I optimize that resource in a better way through a quantum algorithm than by a classical algorithm? So that's, I think, one of the key quantum algorithmic problems. For sure, not the only one, but in terms of practical applications, that's the one of the key applications that people are interested in. On the other hand, similar other kind of tasks are, or related tasks are, someone comes up to you and says, hey, here is a quantum computer. Well, if it was really a large-scale quantum computer, you would be able to verify it by just running Shor's algorithm on it. But again, because of kind of inherent limitations that we don't have quantum error correction, how do I verify that a certain black box is indeed a quantum computer? So coming up with protocols, coming up with algorithms that allow us to verify whether or not indeed a computation being done in a black box is indeed genuinely quantum, or whatever that might mean. More on that by end of tomorrow. For sure, not everything, but at least getting introduced to the idea of what does it mean to be genuinely quantum. So algorithms that allow you to understand that exactly would fall within quantum algorithms as well, that people are working on right now. All right.
Yeah.
And hopefully by the end of tomorrow, I'll try to kind of summarize the distinction between what we think we can do with classical computers versus what we think we can do with quantum computers.
Great. And there was also a question by someone, I can't figure out how qubits are used, but are they actually, what will qubits be presented in, for example, an optimization problem? Stay tuned for that. And next week we will have a keynote on quantum computing hardware. So then you will learn more what the qubits physically are. And then over the course of the next weeks, you will learn more about how then these qubits are used in computations. Over to you, Gibran, for the last 15 minutes of the lecture.
Sure. All right. Yeah. All right. So 15 minutes crash course in the rule book for quantum mechanics in quantum computing. Not a tough job at all. All righty. Anyhow. Okay. Where am I? Here am I. Okay. So just a quick note on the question that I left everyone with. The right answer is definitely there in the chat. There are some kind of slightly right answers there as well. Quite a few people got it. So I'm thinking people who have taken bronze previously have been talking. Anyhow, if you don't have the right answer, and so one popular answer is like, hey, it's just the F matrix that we saw previously, half everywhere. No, the issue is, well, how do I practically implement as someone Ahmed already mentioned in the chat? Well, the only thing you have is this bias point in your hand. How do I apply what would correspond to F on this vector? Right, so you have to come up with kind of an operational process, which indeed at the end of the day, you could think of it as a transformation, but it helps to think of it as really, well, what will I do with this coin? Okay, all right. So the job now in the next few slides is for me to convey to you how the mathematical machinery that we just introduced changes with the quantum rule book. And really, that's the way to think about it. The mathematical machinery that we had was defining for us one way to think about classical computing. Although, someone who's looking at it the first time would be like, hey, this is all just matrix algebra, where is programming, where is computation? Then that's again the fun part of theoretical computer science. It's essentially just math, in our case, linear algebra. Alrighty, so rule number one for us, as Marlu just mentioned, what is a quantum bit? Unfortunately, I will not answer for you the physical part of this question. What exactly is the physical system that corresponds to a quantum bit? What is the reality of it? Whatever that might mean, we'll talk about that a bit later. But we assume now that that physical system X that we have been talking about all day today, what if it's not a physically classical system, or I'm not modeling it using classical physics, but rather this physical system X is a quantum system? What does it mean for that physical system to be quantum? Right? So all that we'll do today in the remaining part is hopefully just identify the mathematical rule book. I will not at all be conveying to you the motivation or the physical machinery in terms of why that corresponds to what quantum mechanics gives us, or why quantum mechanics is correct. That's interesting discussion to be had and lots to be said about it. But what we are doing today is taking the quantum mechanics machinery as a given, and even from that machinery, just extracting 3-4 basic rules. That is all that we need to get started doing quantum computing. So the first rule, the central claim of quantum physics for us, is that when we are modeling our physical system X, that in the classical case was in 2 different levels, let's say. And in the quantum case, now we want to be able to say, hey, still in 2 different levels. Well, just quick recap. In the classical case, it was this vector P, let's say 1, 0, and with 1 minus P, 0, 1, right? So that's one way to write down the vector P, 1 minus P. And the only constraint is that P has to be greater than or equal to 0. This probability is replaced by an amplitude. Why? Again, that's what quantum tells us. That you take this vector decomposition, and this vector decomposition will look exactly the same, except that I will have a nice fun Greek letter psi to represent it, because hey, that's quantum. And rather than using P, I will have, again, alpha, a complex number. The vector remains the same again. And beta, the vector remains the same again. And alpha and beta are complex numbers. They're referring to the amplitude of the system. It could be a spin system, half system. It could be a spin 1 system. Again, that's kind of the physical detail that I will abstract away from. All that I will take here is, hey, I've got a 2-level quantum system. In this case, it will have amplitudes alpha and beta. Well, what exactly are these amplitudes? What are the restrictions on these amplitudes, and how are these amplitudes connected to probabilities? That's exactly what the second rule gives us, which is the Born rule. So the first rule of going from classical to quantum is change the probability to amplitudes. Probabilities were just this nice numbers between 0 and 1. Amplitudes, so far, I've just identified as being arbitrary complex numbers. For sure, there will be a restriction on them. Where the restriction will come from is from identifying, well, how are these amplitudes connected to probabilities? Recall that previously I said that when we have this classical system X, whose probability vector I represent as a vector v hat, then when I look at it, I don't see P, I don't see V, I just see the symbol associated with, let's say, the head, or the symbol associated with the tail, with the corresponding probability P, or the corresponding probability 1 minus P. In a very similar way, the quantum rulebook tells us that when you will look at this quantum system, the probability with which you'll see it in state 0 or state 1 is going to be connected by the absolute value squared of the amplitude. But again, just a rule that we're taking from the quantum mechanics machinery. So if alpha was the amplitude, the corresponding probability becomes magnitude alpha squared. If alpha was a complex number, a plus ib, excuse me, then I can just write it as the magnitudes as a square plus b square, which will be a positive number now, right? It's exactly a probability. And so as some people are already talking about, well, what's the distinction between kind of classical versus quantum? As you can kind of take away from here, is that in the classical case, if you wanted to talk about what's the restriction, it's kind of preserving the L1 norm, right? So P plus 1 minus P has to equal kind of 1. Whereas in this case now, given the rule, which is called the Born rule, in terms of how the amplitudes are connected to probabilities, you get a slightly different rule, which is on the L2 norm rather than the L1 norm. It doesn't mean anything to you, that's perfectly fine. But the point is, rather than just summing up the two numbers, the probabilities, in this case now we take the square and add them up. Now, a simplification for our current purpose, for the entirety of the bronze workshop, and indeed pretty much the nickel workshop as well, we will assume moving forward that these amplitudes are real numbers. It's actually surprising how much of quantum mechanics kind of still works out if you restrict the amplitudes to be real. The reason why we are doing it, because it just simplifies this issue of taking the absolute value squared. You could right now just take the square of the real number. So moving forward, we will assume that the amplitudes are real numbers. So all the equations I will write down after this slide will assume that the amplitudes are real. Just for this slide, for the sake of kind of completeness in the introduction, I give it as amplitudes are complex. Right? So that means a qubit, i.e. a quantum bit, is given by, well, that psi thingy, which is this alpha beta amplitudes, which exactly I can write down as alpha 1 0 plus beta 0 1. But now in a position to write down the restrictions. The restrictions will be that, well, the probability to see it in state 0, which is this alpha magnitude square, plus probability to see it in state 1, which is the corresponding entry for beta, has to equal 1. So this is the quantum normalization constraint rather than the standard probability normalization. Indeed, it is still kind of just the probability normalization, because this thing is a probability, this thing is a probability, and all that I'm saying is that the two probabilities sum up to 1. The key thing that's changing in going from classical to quantum in terms of the mathematical machinery is that we are taking the probabilities and replacing them with these amplitudes. And hopefully that resonates with our start of the session yesterday that, hey, our nice superpower is the ability to manipulate probability, and that's what quantum is going to give us. And that's one thing, again, to keep at the back of your mind in terms of whenever you see something, you're learning something new about quantum, how is that thing allowing us to manipulate probability in a different way, in a richer way than allowed by classical physics. Already to begin with, we see that, all right, when we look at a quantum system, the way the probabilities of what we see emerges comes from this Born rule, which is this taking the square root thingy, rather than just, hey, the probability is just a linear combination, right? So that's kind of a crucial thing. Don't get hung up about the complex part. Drop the I behind. For the entirety of the workshop, we'll work with real numbers. So alpha and beta in real numbers will be sufficient for us. But for sure, not all of quantum mechanics can be derived through this. So, for example, Shor's algorithm uses quantum Fourier transforms that requires complex numbers. So I'm not at all saying that everything in quantum computing can be done with real numbers, but a surprising amount of it can still be done. So now let's write down the definition again, assuming that we have these real definition for amplitudes, real as in real numbers. So when we restrict the amplitudes to be real, then our good old trig functions come in, and those alpha and beta can be represented as just cosine theta and sine theta. Why? We'll see the geometric visualization, if not by end of today, start of tomorrow. And because, well, this corresponds nicely to our trig identity as well. So you really get a nice visualization that a quantum bit with the amplitudes restricted to real numbers just corresponds to kind of a unit vector kind of moving around on the unit circle, right? And so what is quantum mechanics giving us for a quantum bit? Instead of a probabilistic combination, what we get for quantum is the name is we have a superposition. In which case, you might as well ask me, well, what do you mean? What is a superposition? If you ask me the mathematical question, well, I will say, well, this thing is a superposition for choices of theta. Well, mathematically, that's well defined, but what's the physical reality of a superposition? And for me, that's kind of the key underlying question about, foundations of quantum mechanics, quantum information. What's the physical reality of an object, a physical object, when it is in superposition? Now, this may or may not make sense to ask. Indeed, there are people who work in quantum information and quantum mechanics and say, well, that's a meaningless question. And there will be others who will say, well, that's exactly at the foundations of what it means to ask whether or not quantum mechanics is even complete to begin with. Referring to a paper in 1935 by Einstein, Podolsky, and Rosen, asking whether or not quantum mechanics is complete. More on that slightly later tomorrow. But trying to get a better understanding of what superposition is, i.e., what do I mean when a physical system is an alpha 10 plus beta 01? Could I just say, hey, this is in state 0 with probability alpha square and state 1 with probability beta square? It's very enticing to say this, but as we'll see as we go along, the richer machinery of manipulating probabilities in quantum does not allow us to kind of restrict our definition or interpretation of this expression as a just alpha probability alpha square 0 state 0 probability beta square state 1. It's something slightly more subtle, and hopefully I'll try to convey that in our discussions tomorrow. So some people ask, hey, can probabilities be negative? Note over here, we don't have negative probabilities, but the object, the mathematical object through which the probability is emerging, in this case alpha and beta, cosine theta, sine theta, indeed can now be negative to begin with. And this ability for them to be negative is exactly one of the key kind of ways through which we understand quantum mechanics to be providing us this rich feature. You know, go back to your high school classical mechanics, constructive interference versus destructive interference. You could never have probabilities combining together to constructively or destructively interfere because, well, they are always positive. Now you could have probability amplitudes coming in with plus minus signs and canceling each other out or constructively adding up each other. And so that allows for a whole new interference pattern, well, amplitudes adding or subtracting together, which was not possible using classical probability. And that partially, in our understanding, is the source of the power of quantum computing. There's much more to it, but suffice for our today understanding of that. Right? Okay, I think given our time constraint, I should stop here. It's a nice place to stop where we have now introduced the base rule of what it means to define quantum information, i.e. quantum bits. We saw the key rules that change going from classical information to quantum information. Starting tomorrow, what we'll see then is how some of the key rules of, well, what happens when we combine multiple classical systems together? Well, what happens when we combine quantum systems together? Actually, not much will change. The mathematical machinery is exactly the same. The operation I apply is exactly the same. But because the underlying object, the vector that I'm working with, is a different beast, the way I combine it, even though it's still the same, ends up giving me something very different than what the classical thing was as well. Right? So that's something to look forward to tomorrow. And then if time permits, hopefully it does, we'll kind of see nice, interesting quantum protocols in place as well that will motivate to you why quantum protocols do something in a better or in a more interesting way than classically possible. Ideally, we should have seen that today, but because of our time issue, we'll see that hopefully tomorrow. Alrighty. Questions, queries, concerns that I missed? Where is this right, so I think so. We'll talk a bit more about quantum interpretations tomorrow in terms of quantum foundations. And for sure, there are lots and lots of nice ways to talk about interpretations of amplitudes and quantum interpretations. The nice thing that I've taken away from those discussions so far, as most people in quantum computing put it, it's like rather than religiously adhering to one quantum interpretation, the better thing to do is to be a bit more pragmatic and say, hey, for my current task at hand, which interpretation helps me the most? And well, just take that interpretation and use it. If you get some mileage out of it, why not use it? Right? So what exactly do I mean by interpretation and whatnot? Hopefully that will become clear tomorrow. But essentially, we're just asking, what does it mean for this particle to be in superposition? And kind of what I'll end with today is just, why should we ask that question when no one asked, what does it mean for a classical system to be in a probability vector, right? So we